In this next video, we're going to continue looking at the gradient and directional derivatives. So let's consider our directional derivative, which is the gradient of f dotted with a unit vector u. And if we remember another definition for our dot product, that is the magnitude of one of those vectors, so the gradient of f, times the magnitude of the other vector, so the magnitude of u, times cosine of theta, where theta is the angle between those two vectors. Since u is a unit vector, though, the magnitude of u is just 1. So in fact, we just get this formula, the magnitude of the gradient of f times cosine theta, again, where theta is the angle between the unit vector u and our gradient vector of f. So what does this tell us? Since cosine of theta must range between -1 and +1, the maximum value of this expression occurs when cosine of theta is 1. This happens when theta is 0. That means the angle between the two vectors is 0. So this tells us that the maximum rate of change occurs in the direction of the gradient vector of f. And in fact, that maximum rate of change is the magnitude of the gradient of vector f. Similarly, we have a expression for the minimum value, and that is just the negative of the magnitude of the gradient vector of f. And then, furthermore, the rate of change of f is equal to 0 when u is perpendicular to the gradient of f. And we realize that because we have a dot product here between the gradient of f and u. That value is 0 if those two vectors are perpendicular. So that tells us the rate of change, or the directional derivative, is 0 when those two vectors are perpendicular. Now let's do a couple of quick examples, 3 quick examples, in fact. So we're going to find the maximum rate of change of f of x comma y equal to x squared y cubed at some point 1 comma 1. And we're going to find the direction vector u in which this maximum occurs. So first we notice that f sub x is equal to 2x y cubed, and f sub y is equal to x squared times 3y squared. This tells us our gradient vector of f evaluated at 1 comma 1 is, we want to evaluate f, the partial of f with respect to x at 1 comma 1, and we get 2. We want to evaluate the partial of f with respect to y at 1 comma 1, and we get 3. All right. So now we want to know what the maximum rate of change is. This is the direction in which the maximum rate of change occurs, and the magnitude is, so that is the magnitude of the gradient of f and this is the square root of 2 squared plus 3 squared, which is equal to root 13. All right, and so we get to what the maximum rate of change is. We're asking for the direction vector u, so really we mean the unit vector here. So this is 2 over root 13, comma 3 over root 13. And that is the direction in which this maximum occurs, the unit vector in the direction of which this maximum occurs. All right, and that completes that problem. Nope. And now we want to, in this next example, find the minimum rate of change of some other equation here. So f sub x is equal to, this is the same, f of x, y, z here is the same as x over z plus y over z. Y and z are treated as constants when we're taking the partial derivative with respect to x. So that second term goes to 0. The first term is just x over z. The derivative of that with respect to x is 1 over z. Similarly, the partial with respect to y is 1 over z. And then the partial with respect to z is negative of x plus y times z to the negative 2. All right, so what is our gradient vector? Evaluated at 1, 1, negative 1. Well, this is the vector. 1 over negative 1 is negative 1. S sub y is 1 over negative 1 again, so that's negative 1. And then we have negative of 1 plus 1, which is 2, so negative 2 times z to the negative second power. So this is negative 2. All right. Now, we asked what the minimum rate of change was. So this is negative of the magnitude of the gradient of f, which is negative of the square root of negative 1 squared plus negative 1 squared plus negative 2 squared, which is negative of root 6. So that is our minimum rate of change. And what direction does it occur in? Well, it occurs in this direction, but we want the unit vector in that direction. And so we just take all of that. Oh, excuse me, it occurs in the negative of that direction, because this is our gradient vector f here. We want the negative of that direction for our minimum, the direction of our minimum rate of change. So we get 1 over root 6 times the vector 1, 1, 2. All right. And this is the direction in which that minimum rate of change occurs. And then finally here, we have a function f of xy is equal to natural log of x squared plus y squared. We want to find a direction vector u for which the directional derivative of f of xy at point 1, 2 is equal to 0. So first, let's find the gradient of f of xy. Well, this is the partial derivative of f with respect to x in the first coordinate. So that is, so we take that derivative, we end up with 2x over x squared plus y squared. And we get 2y over x squared plus y squared in the second coordinate. Gradient of f, evaluated at 1, 2, is 2/5 over 4/5. So that's our gradient vector. Now we want to find a vector u that is orthogonal to this. So how can we do that? Well, gradient of f dotted with u is equal to 2/5, 4/5 times some vector u, which we can call a, b. Take the dot product here, we get 2/5 times a plus 4/5 times b, and we want this to equal 0, because if they're perpendicular, that means their dot product is 0. Well, just by observation here, you could recognize that this implies that A is 4/5, B is 2/5, so then we need to make one of those negatives. We can choose either one, or we can solve for A in terms of B. So how about we do that? So this is the same as 2/5 A is equal to negative 4/5 B. And if we divide by 2/5 here on both sides, we get that A is equal to negative 2B. So if we just pick anything for B, let's suppose B is equal to 1, then this implies that A is equal to negative 2. This tells us our vector negative 2, positive 1 is perpendicular to the gradient vector here, evaluated at 1, 2. So we have a vector that is orthogonal to the gradient vector at 1, 2, but we want the vector that is the unit vector in that direction. So we need to take the vector -2, 1 and multiply it by its magnitude. And the magnitude of the vector is square root of 5. So we multiply that by the 1 over root 5. And that's actually the end of that problem. We have the unit vector that is orthogonal to the gradient of f at 1, 2. Now, of course, what we actually have written down here is plus or minus that, because you could always take the negative of the vector that we found, and that is also a vector that is orthogonal to our gradient of f at 1, 2. All right. And that is it for this video.